And time for the final talk for this morning before the lunch break. So Meena Mahajan will talk about QBFs and proofs for QBFs.
Thank you. Thank you for inviting me to give this talk. I'm going to be talking about QBF proof complexity, and this is a kind of overview talk of stuff that has happened. Unlike with SAT, QBF proof complexity has a history of only 20-25 years, so there's less to cover, but just give a snapshot of where we are now and what still needs to be done. So the plan of the talk is that I'll try, most of the talk I will focus on the proof complexity perspective for QBF proofs, but a little bit at some point I will also talk about from the QBF solving side, what is it that can be said, and towards the end a little bit from computational complexity, which is the perspective from which I come in actually into this. So maybe initially a little bit of QBF basics, just to make sure that we are all talking about the same thing, and depending on the time at the end, some speculations. So what are quantified Boolean formulas? Well, we know propositional satisfiability. The question propositional satisfiability is asking whether for some propositional formula, there is an assignment to the variables which satisfies all the constraints, satisfies the formula. And this could be restated as a quantified formula by simply sticking in a prefix, which explicitly says, does there exist an x1 and exist an x2 and so on. So all the variables are quantified existentially. And in QBF, the generalization that we allow is that universal quantifiers are allowed as well. So each variable has its own quantifier, which could be either existential or universal. And then we are looking at a sentence of this form. And we want to know now whether the sentence is true or false. So now we wouldn't talk about is it satisfiable or no, because if all the variables are quantified, then it's either true or it's false. And we want to know which of these is true. So expressing constraints in this form, it's not going to allow us to say more things than could have been said with propositional satisfiability, but very often the expression is more succinct. It leads to a smaller formula. It may be more natural, more explainable to write down your constraints in QBF. And so there's good reason to write certain constraints in QBF form rather than as propositional satisfiability. Deciding whether it's true or false is a much harder question. It's piece-space complete. In most of the QBF proof complexity literature so far, we consider QBFs which are in this standard form. So I'll stick to this, but one could also go beyond this. So we will assume that the formulas are totally quantified. There are no free variables. And we also assume that it's in Prinex form. All the quantifiers appear right in the beginning, not interleaved inside the formula. And we assume that the inner propositional formula is in conjunctive normal form. It's a bunch of clauses. And this is just the simplest way of extending, going beyond what has been done for CNF SAT to the context of QBFs. So the two-player evaluation game is something which is very useful to keep in mind when thinking about QBFs, especially when thinking about how one would try to decide whether the QBF is true or false. So there are these two players who step through the quantifier prefix of the formula, and there is a universal player who owns the universal variables. There's the existential player who owns the existential variables, and they have to choose values for the variables in the order of the prefix. Once all the variables have been assigned, then the inner formula can actually be evaluated to true or false. If it turns out to be true, then the existential player has won. If it turns out to be false, the universal player has won on that particular run. But we are not just interested in winning on a particular run. We would like to know whether a player can always force a win on every run, no matter how the opponent plays. And it's always the case that one of the two players has a winning strategy. If it's the existential player, then that's exactly a model or a Skolem function. If it's a universal player, then it's a counter model, a Herbrand function. And we want to determine which of these holds, which of the players actually has a winning strategy. So many of the proof systems that have been designed actually have this thing in mind about looking at strategies, using them to design the proofs, using them to reason about the proof systems. So which is why I just wanted to make sure that this terminology we are all familiar with right in the beginning. Okay, so I mean, that's all I wanted to say about the basic. Let's go to the proof complexity perspective. What is it that we expect from a proof system? So we want proofs to be short, of course. We want them to be efficiently verifiable, again, of course. And these are like even more obvious requirements. We want the proof system to be sound. It should not be able to prove a statement which is actually false. We want the proof system to be complete. Every true statement which is indeed true should be provable in this system. For propositional formulas, there are several proof systems which have been studied with a much longer history than QBF. And as we have seen, propositional proof systems are handling essentially a special case of QBFs. QBFs where you have only existential quantifiers right in the beginning. So now, what we would like to think of for QBF proof systems is how are we going to take existing propositional systems and augment them. It's not necessary that we think this way. We may think from scratch, starting directly with QBF, but many of the existing proof systems actually came into existence by this kind of thought process. Start with a propositional proof system and then add more rules to it so that it can handle the full generality of QBFs. And because in the propositional case, we are trying to prove CNFs false. So, I mean, maybe as a historical accident in QBFs, also the initial proof systems focused more on looking at trying to prove a QBF is false. There is, of course, a duality. True or false are equally hard computationally, but we are going to look at proof systems which can prove false QBFs false. So how are we going to ensure that the resulting proof systems, in whatever way we augment them, how are we going to ensure that they're sound? Typically, this is done by showing that with the augmented rules thrown in, whenever there is a proof, refutation, a proof that a certain QBF is false, by examining that proof, we should be able to extract a representation of a counter model, a Hardness function. Then that would tell us that indeed the formula was false. So many soundness proofs for proof systems have actually followed this way of extracting a counter model from a refutation. How would we ensure completeness? Well, there are 3-4 different paradigms which we have seen in the literature so far. Expansion, universal reduction, literal merging. Maybe it's easier to do this through some figures. So here's a small example, and on this example, I will just illustrate these 4 paradigms in their most basic form. So this formula is saying that there exists an X, so that no matter how you choose U, there is a response Y, which so that the assignment XUY satisfies all these clauses. This QBF is false, and there is a winning strategy for the universal player for choosing U. And here is how I would prove this in some kind of a proof system. The most obvious proof system is expansion, where you just think of the universal quantifier as a conjunction. I mean, that's what the universal quantifier literally means. So you look at the formula starting from U and say that, well, this is the conjunction of the inner formula at U equals 0 and at U equals 1. So that's going to give rise to clauses like this. Y corresponding to U equals 0, the Y corresponding to U equals 1. The other 2 clauses also have their versions with appropriate markers saying which copy they came from. And then it's a purely propositional formula. The universal quantifier has been eliminated, and we can do ordinary resolution or whatever you wish. So this is expansion and resolution. And this finally allows us to derive the empty clause. So therefore the initial formula was false. So this was in fact one of the earliest kind of QBF proof systems. Here's a different style of a QBF proof system where you start off doing resolution as you would in the propositional world, start off with the original clauses, and then you reach a clause which looks like this, X or U. Well, in this, U is a universal variable and it is trailing as far as the quantifier prefix is concerned. This is the rightmost variable. And one can show that it is sound under these circumstances to simply instantiate that universal variable. You can instantiate it to true or to false and add that new clause to your system, and this would preserve a winning strategy of the existential layer. So it's okay to derive this clause from here as well. So this is the universal reduction rule, and using this you can derive an empty clause. So this is the reduction paradigm, and you can use this in combination with other things. This is the expansion paradigm. There's a more complex paradigm which has these kind of strange markers, which says that I can resolve these 2 clauses on X even though U is appearing in different polarities. And this does not mean that I'm going to put U and U bar into my resolvent clause. That would mean that the resolvent clause is true. It just means that at this point, the universal player has a way of assigning values to U. If you are going to win by falsifying this clause, that method can be carried over provided X is 0. If U has a method of winning by falsifying this clause, then that method can be carried over provided X is 1. And so this is a kind of a placeholder for this strategy. So this is the long distance resolution, where you're resolving 2 clauses even though they differ in polarity on more than one variable. And there are systems based on this rule also. This is a 4th kind of paradigm, which is explicitly separating out the existential part and the universal part. On the existential part of each clause, you perform ordinary resolution. And then on the universal part, you start building up what could be a potential counter model. At this clause, the counter model must set U equals 0 if it wants to falsify this clause. At this point, it must be 1. And then you start merging together the partial counter models. So The exact details, the syntax of the rules is not important. Conceptually, what these 4 systems are doing, in some sense, they are different. So this is what I referred to here when I said that there are these 4 different paradigms. And with these, there are various proof systems which have been defined in the literature. This is the vanilla expansion and universal expansion and resolution system. This is ordinary resolution with the universal reduction rule. This is also resolution with the universal reduction rule. These 2 are systems which add that literal merging on top of reduction. This is a system which adds literal merging on top of expansion. This is a system which tries to build up counter models. So there are all these systems which are starting with ordinary resolution for the propositional formulas and augmenting resolution in some way, in different ways. So at this point, you can see that it doesn't really make sense to talk about QBF resolution. There is no one system which is QBF resolution. These are all systems which, when they are given propositional formulas, they degenerate to resolution. So as an accident of history, this has been called Q resolution because this was the first reduction-based system. But I would say that all of these are in some sense QBF resolution. None of them are overly powerful in some sense. So one could also define a reduction system like this, which takes the propositional system of E Frege, not resolution, and adds a universal reduction rule to it. And that system sits on top of all of these. So this is again another sanity check that these proof systems are not doing something which is completely weird. And the extended Frege system with universal reduction does sit inside another formal system, QRAT, which is a format for writing proofs for QBS, generalizing beyond the DRAT format, which has been used for propositional formulas. So this is the simulation order amongst these resolution-based systems. All these simulations, these are systems are going up in increasingly more power. Most of these separation, well, all these separations here are actually exponential. There are formulas which have short proofs here and require exponential length here. Almost all, though not all, almost all of the missing connections are actually non-simulations. We have a whole lot of lower bounds to show that formulas are hard for various systems here. So just a brief comment on this augmenting propositional proof systems. The expansion paradigm would work for any propositional proof system, because expansion just says that you interpret the universal quantifier as conjunction, which indeed is what it is. So you can take any propositional proof system and do expansion, and you would get a QBF proof system. Universal reduction, adding this rule, works for almost all line-based proof systems. But these notions of literal merging or building up counter models, so far they have been done for resolution. It's not even clear that these paradigms can be applied to other systems. So in fact, so these were the 4 kind of ways of extending propositional proof systems that I described, and I don't know whether there are other paradigms as well, which we have not yet discovered, we have not yet thought of. Maybe there are. So this would be something to think about. Okay, so in the simulation order for these proof systems, I'm not going to give like I said, the technical or syntactic details or description of these proof systems, just the ideas behind these. So I mentioned that these separations, that we have exponential separations, which of course means that we have lower bounds. We know formulas which are provably hard for some of these systems. So how do we prove these lower bounds? I just want to briefly go over what are the techniques we have for proving lower bounds for QBF systems. One thing one could do is to simply transfer propositional hardness. Take any reasonable QBF proof system. It doesn't necessarily have to be a QBF proof system which was defined by starting with a propositional system and augmenting it. It could have, you could have come up with a QBF proof system from anywhere. But inside it, you would expect that there is an easily described embedded propositional system. What would your given system P do if it were given purely propositional formulas? The rules, the way it would apply them, that would describe a propositional proof system Q. And inside any reasonable QBF proof system P, where the underlying propositional version is Q, if I start with an unsatisfiable formula F, and I look at refutations of there exists F in P, I look at proving unsatisfiability of F in Q, obviously this is not going to be any easier in the QBF proof system. It cannot do anything more than what could have been done in the underlying base system. So this means that if I have propositional lower bounds, which of course we do, they all directly transfer to the QBF proof systems. So it's not just a question of saying, do we have lower bounds for these proof systems? Of course we do, because sitting inside all of them are propositional systems for which we have lower bounds. What we really would be looking for here is, do we have lower bounds for formulas where the hardness is coming because of the fact that there was quantifier alternation? So it's not purely propositional hardness that we are interested in. And we're not interested in it only because there is another body of work which is already addressing that, not because it's not interesting, but in the context of QBF proof complexity, we want to see where the alternations are adding to hardness. So we would like to understand what is this genuine QBF hardness and what kind of formulas are hard in that sense, not just because of propositional reasoning. So for instance, feasible interpolation. This is a technique which has been used to give many lower bounds for propositional proof systems. And indeed, it can also be used to give lower bounds for many QBF proof systems as well. So the Q resolution, QU resolution, or the long distance work. So for many of them, feasible interpolation as a lower bound technique works. And it shows that formulas which are not propositional formulas, which actually have universal quantifiers in them, it shows that those formulas are hard to refute in these systems. So one would think that, okay, this is not propositional hardness. But actually, if you dig through a little bit more closely, you find that this, in some sense, this is still not genuine QBF hardness, because what the feasible interpolation technique does is it identifies chunks of any alleged proof, which must be very large. And those chunks are actually doing purely propositional reasoning. Even though the formula cannot be stated using without a universal quantifiers, the lower bounds which this throws up is the lower bounds are focusing entirely on parts which have propositional reasoning. The same thing holds for some lower bounds which are proved using prover-Delaire games. So prover-Delaire games have been used to prove lower bounds in tree like Q resolution, one of the weakest systems in that diagram that I had earlier. But again, those lower bounds, even though they are for formulas with quantifiers, they are actually focusing on parts which have propositional reasoning. Yeah.
So here's a very vague question. I'm thinking about this reasonable QBF proof system. I mean, is it clear a priori that, you know, maybe I'm given a tricky CNF formula, but if I'm equipped with QBF reasoning, maybe I could do some amazing QBF style reasoning to actually break the hardness of this purely
so the reasonable
formula.
Is there because of that.
Yeah. So
that so if your formula is purely propositional, but it's in some sense very hard, how could you use QBF reasoning? Maybe if you think of something like an extended resolution system where you're allowed to introduce new universal variables, and then you do QBF reasoning. Well, I don't know what's going to happen. So that's the kind of thing that I have in mind.
So it's sort of related to what you said earlier, that there might be other paradigms that. So
you don't think of propositional. You don't have to think only of propositional plus something more. You may have designed a QBF proof system which started from somewhere else, and then its restriction. I'm not very sure that this will always be the case. Okay, so this slide is about propositional hardness, when it can be transferred, and does it really say something meaningful? And I claim that at least this kind of hardness is not meaningful unless the system is doing something really non-trivial. So in fact, this leads us to the question, what do we mean by genuine QBF hardness? It's such a vague phrase, no? And so if we want to understand this, well, this is at a very intuitive level, this is what I mean by it. So the hardness in refuting some formula in a particular system should not stem merely from underlying propositional hardness. And what do we mean by underlying propositional hardness? You need to formalize it in some way. In expansion systems, the formalization is completely straightforward. You're expanding out the universal quantifier, and so the cost of the quantification is the size of the expanded formula, the part of the expansion that you actually need to use. But in reduction systems, one very neat way of formalizing this has been the use of an NP oracle. And essentially what it amounts to is you discount any reduction steps, any steps that employ reasoning which is checkable by reduction to SAT. So those steps may be involving existential variables, universal variables. That is not the important point. The point is that that entire reasoning you could check simply by a reduction to SAT. And in a reduction-based system, okay, these two reductions are different reductions. So in a reduction system, effectively this amounts to saying you count only the reduction steps. Everything else is propositionally checkable because it's a propositional proof system plus reduction. So you discount the propositional part and just count how many reduction steps are used. In systems which use merging, you would want to discount deduction steps where these partial counter models or partial strategies don't increase in complexity. Then, that part has remained untouched, even if it was not trivial to begin with. Well, whatever non-triviality it had, if it did not change over a sequence of derivations, then that derivation, in some sense, is purely propositional. So these are the parts which we want to discount. And then we want to say, is the formula still hard to refute? So not counting these steps, do you still require a very lengthy refutation? And we do have genuine lower bounds in this sense as well. One could also ask, why do we stop at an NP oracle? Like I've said, QBF is P-space complete. So there's a whole hierarchy between NP and P-space. So you could peg your definition of what is genuine hardness anywhere in that hierarchy. And this has also been done. There are some very nice results which show for various types of oracles at levels of the polynomial hierarchy, you have formulas which are hard to refute, despite the access to that oracle. So this whole notion of formalizing genuine QBF hardness is about understanding the source of hardness. Where is it coming from? Due to what kind of alterations and structure within the formula? And I think there is more that can be done here, but it's really a nice conceptual question. The other way of transferring lower bounds is of obtaining lower bounds for QBF systems is to transfer computational hardness. So if you have some functions which are computationally hard, if you have some languages that are computationally hard, can you use this to design formulas which would be hard for specific proof systems? And in many QBF systems, in fact, such computational hardness can be transferred. And the key idea is this notion of efficient strategy extraction. Every proof that a QBF is false contains, either implicitly or explicitly, it contains information about a counter model. I mean, it's after all, it's proving that the formula is false, so it's proving that there does exist a counter model. So that information is encoded in the proof. Now, how difficult or easy is it to extract that information, to actually extract a description of the universal player's winning strategy? In almost all the proof systems that we know, the actual extraction works quite efficiently. So now the general template for these kind of lower bounds is like this. You start with a proof system and you identify the correct circuit model corresponding to this proof system. So your circuit model may be polynomial size circuits, maybe polynomial size constant depth circuits, maybe decision lists, decision trees, branching programs of a certain kind, whatever. For every proof system, try to figure out what is the correct circuit model. And what I mean by correct is that whenever we have a refutation in this proof system of a certain size, we should be able to extract from this refutation a description of the counter model in that model, in the model M. So the circuit model computes the winning strategy of the universal player. And the description of the circuit in M should be polynomial in the size of the refutation. Now, if we can find this, then the next thing we would want to do is to find some Boolean function which has polynomial size circuits, but which is hard in this circuit model. So the circuit models will be typically much more restrictive than polynomial size circuits. And you want to find a function which is hard for that model. And now it's completely straightforward. We can construct false QBFs. In fact, they are sigma-3 formulas, which in which there is just one winning strategy for the universal player. That winning strategy is forced to compute F. If the winning strategy chooses for a universal variable, a value other than the function F computed on the existential variables, then the existential player can win. So the formula somehow has to assert that F is computed on the existential variables. This can be done. It's not very complicated. And once you do this, now you have, did I go to the next one? Yeah. Now we immediately have lower bounds, because putting together these two ideas, any short refutation for this corresponding sigma-3 formula would give rise to a small circuit computing F, but we know that there are no small circuits computing F of that type. In particular, if you look at Frege style proof systems, Frege with the universal deduction rule thrown in, and maybe the Frege style systems are looking at a restricted kind of circuit, then this very nice work done by Olaf and Jan, they showed that there are only two sources of hardness in such systems. Either there is a propositional related formula, which is hard, or there is a lower bound for the circuit class C. The propositional formula and this lower bound, they are also very nicely stated here. From any proof in such a QBF proof system, we can efficiently extract a set of witnessing circuits So these witnessing circuits are actually computing the winning strategy of the universal player, the Herbrand function, and a propositional proof that those circuits actually constitute a winning strategy. So from any refutation, I can extract a description of the counter model and a validation that this is indeed a counter model. So if either of these two tasks is hard, then there is no short proof. And in fact, with this template, now it turns out that we can even give lower bounds for Frege plus reduction systems where every line must be an AC0 mod 2 circuit. Now, this is a famously open problem in the propositional case, but in the QBF world, yes, we do have such lower bounds. And it's simply because we do have circuit lower bounds here. So we know that there are not going to be any witnessing circuits of this kind. So this is a different way of transferring computational hardness. A third way of transferring computational, well, not a third way, but a third viewpoint on this. So in the propositional world, the size width relation has played a very prominent role in proving lower bounds. And so it was very natural to explore whether there is a similar such relation in the QBF world and would that lead to lower bounds. Well, quite some years ago, we realized that this does not work for Q resolution. Size width relation fails completely. And that seemed to be a bit of a stumbling block. But a little later, a few years later, we realized that in fact, there is a modified adaptation of that relation, which does work for QU resolution. This is resolution plus reduction. So a modified version of the size width relation, which actually takes into account the alternation depth, also holds here. It does give lower bounds for bounded alternation formulas, not for arbitrary full QBF. And the main idea behind this proof, again, turned out to be a circuit characterization of this proof system. So even though it looks like it's a different approach via the size width bound, it's finally via circuit characterization and transferring a circuit lower bound. So this method also it fits the template of transferring a computational hardness. If the winning strategies are hard to compute, then related formulas will be hard to prove false in the system. Is there a third source of hardness? So there's propositional hardness, there's computational hardness. It looks like there may be a third source of hardness, semantic hardness. So there are various systems which are not as strong as the Frege plus reduction systems, for which it can be shown that certain formulas are hard. These are formulas where there is no underlying propositional hardness and where the winning strategies are completely trivial to compute. So it's not computational hardness of the winning strategy. And the way these lower bounds have been proved, there's this series of papers which so one of them looks at the cost of a formula. This is a semantic measure of the formula. I'm not going to define it. I just want to put out these terms here to say that there are these measures that can be defined. And there is a relation between the size of a proof, the cost of the formula, and the capacity of a proof system. And this is used to give lower bounds for many reduction-based systems. There's a different semantic measure called a strategy size or the strategy weight of a QBF, which if it is large, then one can show lower bounds in expansion-based systems. There's yet another measure called the gauge of a formula. If that is large for typically a sigma 3 kind of formula, then it would be hard in yet another kind of system. So these are measures of the formula. And what this approach is saying is that if these measures are large, then these formulas will be hard to refute in a corresponding proof system. So since these are measures of the formula itself and they are not computational measures, these measures could be large even if the winning strategies are trivial to compute. So it looks like it's a different source of hardness. It's not computational hardness. So this is the question: is it really a third source? And at least in one case, it looks like actually it is not a different kind of hardness. It's again the same thing. So there are these so-called equality formulas where all the semantic measures are very high. Cost is high, weight is high, gauge is high. So they are high in, therefore these formulas are hard in multiple proof systems. Winning strategies are completely trivial. You just, each universal variable U copies the value of an earlier existential variable. No computation is required. So one would think that there is no question of computational hardness to be transferred because there is no computation required. But it turns out that there is a computational model, which is multi-output decision lists, where these strategies are hard to compute. And they are hard to compute because this computational model expects the entire block of universal values to be given at one shot. So when we say something is computationally hard, computationally easy, it's not automatic that we understand exactly what is hard and easy. It depends so much on the model, and some work is required to find the right model. So this was a bit of a surprise at this point, that what seemed to be a hardness stemming from a purely semantic measure actually can be interpreted as a computational hardness. So maybe there are more such connections to circuit models and proof systems yet to be discovered, and it would be nice to clean up this picture. So this was, I mean, most of the talk was about this proof complexity perspective. Some of the questions, well, the first one is designing different proof systems starting from the game semantics of QBF. So not starting from propositional proof systems and building up, but directly thinking in QBF terms. Algebraic reasoning, there are not too many QBF proof systems. Of course, there is polynomial calculus plus reductions, but static proof systems, I do not know what is the analog. This is, in my opinion, a really glaring area where we need to do more work, identifying more candidate hard formulas. There are very few formulas, and we're just playing around with them and tweaking things here and there. We should be able to understand hardness better, and for that we need more candidate formulas. So how would one come up with candidate hard formulas? One is that we should be exploiting the succinctness of QBF over the propositional case. The other is, are there mathematical principles that are more naturally, so in the propositional world, these are the usual suspects, you know, pigeonhole principle, sight and chessboard, they keep cropping up. What are analogous things which should come up in the case of QBF? So Stefan already mentioned some mathematical theorems which are more naturally encoded as QBF, and can we try and formulate candidate hard formula families based on these? That would be something to think about. Based on computation, of course, this is something that has been done and more can be done here. Another question which could be looked at a little bit more is formalizing the random formula model. Some work has already been done here, but I think there is a lot more to be done. Understanding whether most formulas are hard and from what distribution they are hard. So there's some stuff to be done here. This I've already mentioned, characterizing proof systems via circuit classes, understanding the sources of hardness. So far I've mentioned 3 sources, and I'm already wondering whether the third source is actually a manifestation of the second, but maybe there is even a 4th source and 5th source that we don't know about. Okay, so this is about the proof complexity part. Let me move to the third part from the, yeah, okay, there's a question.
And just curious about, I mean, one source of in proof complexity, propositional proof complexity of one source of hardness, which would be like, yeah, pigeonhole principle, handshaking lemma, those kind of things. But there are also, like, you can take NP complete problems. People have been studying clique and coloring, vertex cover.
Right.
Do you have like a corresponding...
What I would say is based on computation. That, you know, here you have p-space completeness.
Yeah. Are there any results for like a nice encoding of a p-space complete problem, and this is hard for proof system such and such?
Not that I know of. Do you know any better, Olaf?
No.
No. Okay. Good. Yeah. I don't know. So this has not been done. The computation-based hard formulas that we know are the ones which are using circuit computation hardness, but they're not using uniform hardness. Okay. So next segment with QBF solving. This I'll spend 5-6 minutes on this. So we have heard a lot about CDCL. So far, it's a non-deterministic template for an algorithm which can decide satisfiability, and it's a template. When you actually instantiate it, you will plug in various heuristics, and we know that CDCL is equal to resolution. There are, for every resolution refutation, there are choices that could be made for the non-deterministic inherent non-determinism, so that the CDCL run will be of the same length with a polynomial blow-up. Is there an analog of this in the QBF world? That's one question that is very natural to ask for. So there are QBF solvers being built. They are again based on CDCL. And is there an analog saying that QBF resolution is equal to CDCL? Well, this begs 2 questions. Firstly, when we say QBF resolution, which one do we mean? The figure that I showed, there were multiple systems which were resolution and an augmentation to QBF. So it's not even clear which is the correct proof system. But even more, it's not even clear what is the correct quantified CDCL algorithm. So you have the CDCL algorithm which works for the propositional formulas. You want to lift it to QBF. Again, there are potentially many ways in which this can be done. So which one of them is truly Q-CDCL? Maybe we don't have to say that this one is the correct one. Maybe all of them are fine. But then do we have equivalences for each one of them to some kind of resolution-based system. I think it's natural to expect that there should be some such equivalence. And the question is to explore what these equivalences are. So having said this, maybe I should have a brief slide describing what goes on in QBF solving. I know very little about QBF solving. I know that it is done. And I know that there is a QBF competition. There are solvers based on expansion. And that would be a natural thing to do, which is because, like I said, the semantics of an expansion-based system is the most obvious one. It's also natural to expect that an expansion-based solver would somehow be limited. It would have to expand the formula, and that itself would incur a high cost. So some theoretical studies have been done. There are the expansion-based proof systems explain the runs of these solvers. But I think most of the QBF solvers that are actually appearing at the QBF competition are based on CDCL. And there are many more questions to be asked apart from the questions which are asked in the case of the propositional world. There are more questions which arise because we are dealing with QBF. In particular, the reduction policy seems to, almost all the existing solvers, I think, use reduction, but there are things which could change. So maybe it doesn't make sense for me to try and describe these terms now, just to say that there are more parameters. And of course, that means that there is more complexity. There are heuristics which have been used in many of these solvers. In particular, dependency schemes, I think, are used in almost all of them in some form or the other. And what these dependency schemes do is to say that in the QBF, the variables are listed out in the quantifier prefix, and we think of the truth or falseness of the QBF based on a two-player game. So each player chooses the value of his or variable, knowing the values of all the preceding variables. But maybe to actually win the game, when I am choosing the value of this variable, I don't even need to know all those preceding values. So does my winning strategy actually depend on the preceding values? So one could talk about a really required dependence or a dependence which is there just because by accident they were before this in the prefix. So dependency schemes try to eliminate dependencies which are spurious, which are there because of a linear order of the variable, but which play no role as far as actually constructing a winning strategy is concerned. So somehow you can just analyze the structure of the formula, the clause variable incidence, the connections between various variables through resolution paths, and figure out that certain dependencies which come from the linear prefix are immaterial and discard them. So then you can use that along the way in the CDCL solvers. There's also dependency learning, which takes a diametrically opposite view. Instead of starting with all the dependencies from the prefix and then throwing out some, you start assuming there are no dependencies whatsoever. And then when you start trying to construct a refutation, you run into problems and you say, aha, this means that there must be a dependency. You add it to your set. So these things are being done in the solvers. There are many complicated ways of doing this. And I would like to highlight just two of these equivalences here with all this complexity of the different parameters that could be thrown in. Here is one expansion-based system, which is explained by this proof system. And there is one particular kind of CDCL style solver whose runs give rise to proofs of this form. But this is by no means an equivalence. It's just saying that this is contained here. So the equivalence question we are still very far away from. There are many more proof systems here. Are there solvers corresponding to those? As far as I know, they are not implemented. Some surprises or maybe even distractions, one could say, in this context. Evaluating the QBF is an inherently sequential two-player game. So one would think that any CDCL style run in a trail should make decisions in at least respecting the alternation order. Within a block, maybe you can choose whatever order of the variables, but if you have a universal variable depending on previous existentials, you should not decide it before knowing these preceding values. So it seems like level order is a completely reasonable policy for the decision policy. And the surprise is that proof theoretically any order has also been shown to be sound. Another thing is that solvers don't know a priori whether an input is true or false. So of course, you treat every assignment as a conflict. And so if you end up with an assignment which falsifies some clause, then from that you can learn a cube. If you end up with an assignment which falsifies some, which satisfies all the clauses, then you know that this trail cannot form part of a winning strategy for the universal player. So you learn a cube. So you should really be learning clauses and cubes on every trail. And this is indeed what solvers do. So And it's not conflict-driven clause learning. The C is a bit overloaded. It's conflict-driven clause cube learning. So maybe just CDL. And it looks like, well, for false QBFs, you don't need to learn cubes. Learning clauses would be enough for completeness, but learning cubes actually helps. Similarly, dependency schemes, whether you choose to use them or no in your solver, well, it can never lengthen a proof. If you look at a proof system, dependency schemes, if at all they help, they don't harm. But when you look at Q-CDCL algorithmic runs, some recent work that we have done actually shows that whether you use or don't use a dependency scheme can make the systems incomparable. So it seems very counterintuitive that using a dependency scheme can actually slow down a solver. So some questions which arise from here very briefly. Can we implement solvers based on those more complex proof systems that were sitting on top? Or are they just proof theoretic constructs that are of no relevance to practice? This I do not know. Can we actually understand what are the proof systems that characterize heuristics which are used in practice? Again, this we do not know. Dependency learning, as far as I know, has not been captured in any proof system so far. So this was a very brief run through of the solving perspective. And now I still have this one thing. So I'm going to take 1 minute, 2 minutes maximum. I think 1 minute. Okay. The Cook-Reckhow framework. Okay. The Cook-Reckhow framework says that polynomial size proves polynomially verifiable. This is NP, but if you can also do this for co-NP, then co-NP equals NP. So it's about complementing non-determinism. With P space, the situation is different because P space, NP space, co-NP space, we already know they're equal. So what happens if QBF has poly-size, poly-verifiable proofs? It means that P space is equal to NP. And I prefer to read this as NP space is equal to NP, because then what it tells us is that such proof systems, the existence of such proof systems is a question about whether non-deterministic space can be collapsed to time. On the other hand, if you go all the way up to any XP, then provably we know that there aren't polynomial size, polynomial time verifiable proofs that will contradict the time hierarchy. But what we can ask for with any XP is, are there exponential size proofs which are verifiable in time, which is polynomial in the length of the proof? And these exist for any XP by the definition of non-deterministic computation. But do these kind of proofs exist for co-NP? If they did exist, then co-NAXP would be equal to NEXP. And this is again similar to the original Cook-Reckhow question, a question about complementing non-determinism. So the reason for this slide is to say that the question at QBF is fundamentally different. It's about collapsing space to time, not about complementing non-determinism. And because it is fundamentally such a different question, we should be thinking about QBF proofs in a completely different way, not in the style that has been used there. There was one slide here which I had about dependency QBFs and multi-party games, which I won't describe, but I think this is a nice message to take. NP corresponds to one-player games. P space corresponds to two-player games. NEXP, the next, exponential length proofs, that corresponds to multi-party games. And you could use that to design solvers for DQBFs. If you ask me, I find it hard to believe that DQBF solvers are for real. I mean, NP is bad enough. It's hard enough. We are thinking of P space proofs, and then there are people who are building DQBF proofs. There are DQBF solvers which are currently being written. And maybe the questions that should be asked there are, what fragments of DQBF genuinely give you the succinctness to encode your constraints? So actually, this is one question which I think is interesting. NEXP DQBF is the complete problem, but another complete problem is succinct SAT. So each DQBF is a succinct representation of CNF SAT. So if we can talk about succinct representations of formulas, we should ask for succinct representations of proofs, and maybe that will throw up some new ideas. So these are the questions which come from the computational complexity perspective. And with that, let me end with my last slide.
Any quick questions?
Thank you. It was great. I was wondering if you could say a little bit more about succinctness, because in recent years there have been results for other systems where there would be lower bound proven for something that's not propositionally expressible. Mm-hmm. Is there something like that happening in the QBF world, where you could talk separately about things that you could technically write down, maybe even as CNFs versus things that you absolutely have to write down as QBF?
So, I mean, how would you explain the result that succinct sat is any XP complete?
Oh, this is one, yeah.
So there the formula itself is being represented succinctly, but that takes you all the way to any XP. And I think your question is about P space. Is it?
Yeah, the question is about interplay between expressibility versus hardness of solving.
Yeah, so not expressiveness, but succinctness.
Yeah, succinctness.
Because
yeah.
we're still expressing the same set of constraints. It's still propositional logic.
Yeah, yeah.
Yeah, so this is something that we don't understand, I would say. You want to know how the succinctness plays into producing proofs which are hard to, in producing formulas which are hard to refute. I think that's just restating the question that we face currently.
Okay.
Thank you, Meena, for a great talk. Just one comment about the DQBF solvers that are being built, you mentioned. People build program analysis tools for undecidable problems. Just letting you know that, that doesn't stop,
that doesn't stop the engineering enterprise has to go on. I agree. I guess the question that is being asked there is different. I mean, when you're building that solver, you don't expect to really solve all instances of DQBF anyway. You expect that the instances on which you would want to use this solver are arising from some natural setting where there is some obvious structure and you want to exploit that structure. So understand that structure better.
These are worst case complexity you're talking about, right?
Oh, so actually, this question is to do with a question which you had asked me earlier, because it is not just about worst case.
Okay.
A little bit like so your question, you want to ask about average case?
Yeah, I mean, in the context of what Vijay also said, I mean, any XP complete DQBF, this is the worst case complexity. And I mean, you really require to craft an example to hit that worst case complexity. So.
Oh, I see. Okay. Okay. So that this is a comment in that sense. So, I mean, I don't see how proof complexity is going to give answers easily formulated.
Can we talk about complexity measures which are not worst case complexity? Because that might actually be very useful to understand structure of problems.
Yeah, so hardness of random formulas, for instance.
For instance,
that would be one example. Like if most formulas are hard, then in some sense it's like it's answering this question, right?
Okay.
I don't know what are the other ways in which one could choose to answer this.
What I'm saying is worst case complexity doesn't always help. And it shows that there is something out there, maybe some very.
But worst case complexity is already a computational construct. I mean, the proof complexity world, I do not know what is the. Yeah, okay. So maybe that is your question. What is the analog?
Yeah.
I do not know.
All right. Thank you, Meena. It's time for lunch and we will reconvene at 2 p.m., right?